admire the whole Ukraine algebra community for keeping the tradition of this event also in these difficult years. Some convention about this talk: K will be an algebraically closed field, A a finite dimensional algebra over K, modules will be usually left mod A modules, and N will always be the number of simple left A modules up to multiplicity. The letters T, X, Y, and so on denote finite dimensional left A modules. If M is a module, add M denotes all the finite direct sums of summands of M. About notation, when I write a module in the form M is the direct sum of M1, M2, and R, and they say that M is basic or indecomposable or multiplicity free, I mean that the summands M1, M2, and R are indecomposable, pairwise non-isomorphic. That is, Mi is not isomorphic to Mj if I is different from J. Another definition used in the following is that of self-orthogonal module. A module M is self-orthogonal if for any I positive integer I, the groups xi and 0. About the title and the talk, the title of my talk is the title of the last paper, paper number 4 in the abstract. This paper is available on the archive. And the theorem in the title will be theorem 3 in my talk. I'll explain the meaning of the tau in the title. Tau is the Auslander-Reiten translation, and the Auslander-Reiten translation, tau usually denote two things. First of all, tau will be a bijection between some indecomposable modules, but tau will also denote a map induced by this bijection between finite dimensional modules. The bijection tau has the following property. If M is an indecomposable non-projective module, then tau sends M to an indecomposable non-injective module denoted by tau M. There is an important relationship between M and tau M because there is a short exit sequence which does not split, such that the first non-zero module on the left is tau M, while the last non-zero module on the right is the module M. And the module in the middle, and so since the sequence does not split, in the middle we do not have the direct sum of M and tau M. The map tau has the following properties. Tau of any projective module is the zero module. And the action of tau on a direct sum of indecomposable modules, M1, M2, and N, is the direct sum of the images of M1, M2, and N under the map tau. The bijection tau is described by a usually very large quiver, which is called the Auslander-Reiten quiver, denoted by AR in the following. The vertices of the Auslander-Reiten quiver are the indecomposable left A module over the algebra A, while the arrows in the Auslander-Reiten quiver describe the reducible maps, which are some maps which are either injective or surjective. I will denote with 1, 2, 3, and so on, the simple module corresponding to the vertices 1, 2, 3 in the path algebra given by a certain quiver. On the other hand, the picture in the last line denotes indecomposable modules. For instance, the two red modules, 1, 2, 1, 2, 3, are uniserial modules of length either 2 or 3, while the green module is a module with a decomposable socle, the direct sum of 2 and 3, and a simple top 1, while the blue module denotes an indecomposable module with simple essential socle 4, such that the quotient with respect to the socle is the direct sum of 2 and 3. An example to explain the convention used to describe indecomposable modules. I take in this first example, A is the 6-dimensional algebra given by all Lawyer triangular matrices, 3 by 3 Lawyer triangular matrices. This is the path algebra of a thinking quiver, 3 vertices and 2 arrows in the same direction. This algebra A has finite representation type, so the list of indecomposable left modules is finite, and we have exactly 6 indecomposable modules. The first 3 written here, the blue, the green, and the red, are the indecomposable projective modules of the algebra A. And then there are 2 indecomposable modules which are injective and which have dimension 2 or 1, the injective I2 and I1. And finally, there is another simple module which is neither projective nor injective, and it is the quotient of the projective P2, the 2-dimensional green module, with respect to the socle. Now, I will show the picture of the Auslander-Rayton quiver. This quiver has exactly 6 vertices. On the left-hand side, there are the 2 projective modules, and on the right-hand side, the 3 injective modules. The modules which are not projective are 1, 2, 1, and 2, and the action of tau is described here. So tau of m is, if it exists, if it is different from 0, the indecomposable on the left-hand side. The tau, this quiver admits 3 tau orbits with either 1 indecomposable module of dimension 3 or 2 indecomposable modules of dimension 2, 1, 2, and 2, 3, or 3 indecomposable modules, that is all the sample modules which are on the bottom. Now, another example, in this case, we have again an algebra of dimension 6, but this algebra is not hereditary. And we may describe this algebra with a quiver at the bottom with 3 vertices, 2 arrows, 1 loop, and the property that any path of length 2 is equal to 0. That is, A2 is 0 and AB is equal to 0. From the point of view of matrices, A is the algebra of all 4 by 4 matrices written here. So in this case, there exist exactly 9 indecomposable modules. 3 indecomposable modules are projective, 1, 1, 3, 2, 3, 3. 3 indecomposable modules are injective, and we are the uniserial module 1, 1, the simple module 1, and the indecomposable 1, 2, 3. And then there are 3 other modules which are indecomposable, but neither projective nor injective. The module 1, simple module 1, the uniserial 1, 3, and big module of dimension 4. The picture of the Auslander-Rayton quiver of this algebra A is at the bottom. And in this case, we have a closed path from the module 1 to the module 1. We have to identify the simple module 1 on the left with the simple module 1 on the right. Since there are 3 simple modules, there are 3 indecomposable orbits with respect to the map tau, and one of them has 5 indecomposable modules, the blue modules, and 2 of them has exactly 2 indecomposable modules, the red one or the violet one. Now, about this paper, this is a non-technical outline of my talk. The starting point in theorem 1, 2, and 3 will be 2 different modules or 2 different pairs of modules, plus some properties that I will explain later, constructed with n indecomposable modules, x1, x2, xn, pairwise non-isomorphic, and other 2n indecomposable modules, y1, y2, yn, again pairwise non-isomorphic. What happens, the surprising fact, is that always there is at least one permutation S in the symmetric group Sn, such that for any I, if we compare xi and ysi, the corresponding module, so a yellow module and a green module, we have that these 2 modules cannot be ingredients of a module or of a pair of modules with the same properties of the 2 objects we started with. The 2 objects, either modules or pairs module, will be a tilting object, a very concrete tilting object. The prehistory of theorem 3 are theorem 1 that I presented 2 years ago at this conference, and theorem 2. Theorem 1 and theorem 2 are contained in 2 joint papers with a mathematician from Turkey, which is Melis Tekin Ekçin. 2 surprising facts in all the theorems are the following. The key role played by a combinatorial lemma without tilting theory, without tau tilting theory, and without modules at all. And another fact is that to prove theorem 1 or to prove theorem 2 and theorem 3, what we have to do is the following. We have to check if some indecomposable modules are isomorphic or not, or non-isomorphic, and if some groups are different from 0, are 0 or different from 0. In theorem 1, the important groups are X1 groups. In theorem 2 and theorem 3, the important groups are Om groups. And the relationship from the first, the second, and the third theorem is that theorem 3 implies theorem 2, and theorem 2 implies theorem 1. I will describe in the tutorial example what happens. In the first example, with the hereditary algebra given by quiver 1 to 3, if we consider the direct sum of the 3 projective modules, and we denote by X this module, and we consider the direct sum of the 3 injective module, and we denote by Y this module, we have that these 2 modules are all basic, self-orthogonal, and they are the direct sum of 3 indecomposable modules. So the number of their indecomposable summands is equal to the number of simple modules. On the other hand, if we consider the following direct sum, we obtain some modules which are neither basic nor self-orthogonal. For instance, the direct sum of x1 and y1 is projective-injective, hence self-orthogonal, but not basic. On the other hand, the direct sum of x2 and y3 and of x3 and y2 are 2 basic modules which are not self-orthogonal. That's why we can say that if S denotes the permutation 2, 3 in the symmetric group F3, then for any I, we have that the direct sum of xi and ysi is not basic plus self-orthogonal. Similarly, in example 2, again, over this non-hereditary algebra, if we consider if X denotes again the direct sum of a three indecomposable projective module, and if we denote by Y the direct sum of the following three indecomposable modules, we have that X and Y are both basic. X is projective. On the other hand, Y is a self-orthogonal module of projective dimension at most 1. However, in this case, we have that if S is the permutation 1, 2, then for any I, the direct sum of Xi and YSi is not a self-orthogonal module. And I will show this fact in the Auslander-Rayten-Quiver. So this is again the Auslander-Rayten-Quiver of the algebra in example 2. And if we look at the position of the two green modules, we see that the x1 of y2 and that x1, y2, x1 is different from 0. While if you look at the position of the two red modules, we see that another extension, the red extension is 0, and the same happens for the extension of y2 and x3. Now, the precise definition to state theorem 1, we say that a tilting module is T is partial tilting if its projective dimension is at most 1, and if x1 tt is equal to 0. With this definition, we say that a module T is tilting if it is partial tilting, and if up to multiplicity, T is the direct sum of n pairwise non-isomorphic indecomposable module. So T is T1 to the M1, T2 to the M2, Tn to the Mn, where the Mi are at least equal to 1. An important fact from tilting theory used in our proof is due to Ringel, and it says that if T is a tilting module, and if also the direct sum of T and S is a tilting module, then we have few choices for S, because S is in the class add T. So S must be a direct sum, a finite direct sum of summands of T. And now, theorem 1 says the following. If we have two basic tilting modules, X and Y, what happens is that, of course, the direct sum of X and Y is a direct sum of any indecomposable modules, and all these indecomposable modules are partial tilting. However, there is a permutation S in the symmetric group Sn, such that for any I, the direct sum of Xi and YSi is not basic plus self-orthogonal. And this is exactly what I've shown in the two first examples. Now, two definitions for theorem 2 from tau tilting theory. A module T is tau rigid if T tau T is equal to 0. And with this definition, T is tau tilting if it is tau rigid, basic, and if N is the number of the indecomposable summand of T. The relationship between these four classes of module is that partial tilting implies tau rigid, basic tilting implies tau tilting. And an important result from tau tilting theory due to Adachi, Yam, and Rayten says that if T is tau tilting, and if the direct sum of T and S is tau rigid, then the summand T belongs to the class add T. And after my talk at the last conference, I received an email from Ramin Ebrahim, and he gave me a good suggestion to look at the tau-rigid module instead of X-rigid modules. Theorem 2 says the following. If X and Y are two tau-tilting modules, then when we build the direct sum of X and Y, we have a direct sum of 2n indecomposable modules, and all these indecomposable modules are tau-rigid. What happens is that there is a permutation S such that for any I, the direct sum of Xi and YSi is not basic plus tau-rigid. An example, if you take this non-hereditary algebra and we look at the Auslander-Reit-Quiver, we can consider the following examples of two tau-tilting modules which are not tilting. X is the direct sum of 1, 2, 3, 1, 3, 3, 4. Y is the direct sum of 1, 2, 3, 1, 2, 2, and 4. What happens is that if you apply tau to X and Y, we see that we have no map from X and tau X and no map from Y and tau Y. That is, X and Y are two tau-tilting modules. However, since 1 and 1, 2 have projected dimension 2, X and Y are not tilting. And if we look at the direct sum of X1 and Y1, we have a module which is not basic. While if you look at the direct sum of X2 and Y3, X3 and Y4, X4 and Y2, we have a basic direct sum which are not tau-rigid. And so the permutation in theorem 2 in this case is the permutation 2, 3, 4. Another example with an algebra of infinite global dimension. We take the algebra given by this quiver without path of length 2, and in this case, the direct sum of 1, 2, 2, 3, and 2, and similarly, the direct sum of 2, 3, 3, 1, and 3 are tau-tilting modules. And the permutation in this case is the permutation 1, 3, 2, because these direct sums are not tau-tilting. What happens is that since X1 is a projective injective module, the analog of theorem 1 does not hold for these tau-tilting modules. Now, the last definition for theorem 3, not of modules, but of pairs of modules. A pair TP is tau-rigid if the module T is tau-rigid, the module P is projective, and if there are no maps from P to T. Moreover, a pair of the form TP is a tau-tilting pair if it is tau-rigid, and if the direct sum of T and P is a basic direct sum of n indecomposable modules. We use again a result by Adaki, Yama, and Reiten, and I only note that any tau-tilting module T has the property that T0 is a tau-tilting pair. On the other hand, there exists a tau-tilting pair which are with a P different from 0. And for instance, if you take this thinking diagram with two vertices, we have that the pair 1, 2 is a tau-tilting pair with P different from 0. So a proper tau-tilting pair. Theorem 3 says the following. If you have two tau-tilting pairs, Tp and T prime P, if X is the direct sum of T and P and Y is the direct sum of T prime and P prime, then X direct sum Y is a direct sum of 2n indecomposable modules. And in this case, there is a permutation S such that for any I, one of the following pairs is not basic plus tau-rigid. A pair is basic if T plus P is rigid. And the pair are the three pairs that we can construct with Xi and YSi. In the first pair, the first component is 0. In the second pair, we have that we have the module Xi on the left, the module YSi on the right, and YSi is a direct summand of P. In the last pair, YSI is on the left and XI is on the right, and XI is a direct summand of P. A remark, if X with the usual hypothesis on X, Y, and S, if X and Y have a common indecomposable summand, that is, if Xi is isomorphic to Yj for some J, then in theorem 1 and theorem 2, we are lucky because we can conclude that Si is equal to J, while the same conclusion does not hold in theorem 3, and I will show you an example. Again, a Dynkin diagram, so an hereditary algebra, and if you consider the pair Tp and the pair T prime P, they have a common summand, but what happens is that S1 cannot be equal to 3. In this case, we have two possible permutations, the permutation 2-3 and the permutation 2-3-1. But this is not strange. Usually, you may have many choices for the permutation S. And this happens because there are usually many admissible candidates for the element S1, S2, Sn. More precisely, if for any I we denote by Fi the set of admissible candidates for Si, then what happens is that for any m from 1 to n, if I1, I2, Im are n different indices between 1 and n, the union of the subsets Fi1, Fi2, Fim is large enough because it has at least n elements. And this is the important reason why we can find a permutation S such that Si belongs to Fi for Ni. And this is the combinatorial lemma. And an example, if you take, for instance, again, the Kronecker algebra, we have that F1 and F2 are as large as possible, and they have two elements if you use the tilting projective module X and the tilting injective module Y. Thank you very much for your attention.